we go. Okay. So there we are. So I came up with a differential equation the other day. And what we did was we started with thermal physics that we had all seen in physics 4B. So the first thing was just energy flowing in or out of a body of mass m, thermal energy. And the second law was heat transfer. And I'll just say magnitude K, A, delta temperature divided by delta thickness of that object we had there. And then we used a couple of continuum ideas, and we ended up with a differential equation. It looked like this: dT temperature. Actually, this should have been a partial. That was a partial derivative. dT times. I had a constant alpha and a del squared of temperature. And what was that alpha? Was that K? C over rho, or rho C?
A over rho C.
K over rho C, good. K over rho C, rho is the density. And this del squared was div grad. Div grad. And then there's going to be a way to solve this differential equation, but what we're going to do is actually come back and cover all the material that it would take to understand that derivation properly. Okay. So this is a good time to review multivariable calculus and then the integral theorems that go with it. Good. So that's as good of a motivation for this as any. We need the multivariable calculus moving forward in this class anyway. We want to get to linear algebra. We want to have the whole multivariable world at our disposal. On the other hand, this one could be and can be and will be solved using the techniques we've already developed. Okay? So the complex analysis techniques will allow us to solve that. And so our next topic here is going to be multivariable calculus. I'll start with one variable once again. So this is what we started this semester off with. We have one variable and then we'll move. We have one variable, we have, f of x is a function. We have the derivative dy dx equals f prime of x, there's nomenclature. And if we have a function, we can graph it. And we can analyze it, local minimum, local maximum, slopes, all those good things we have with one variable. We also have the chain rule. Physics, we will often have the time derivative wanna do this in many variables. And you know, I'll even write for this review of one variable, that if we have integration, then we would have integral f of dx a to b, and I'll just give a sort of visual, you know, the area under the curve from a to b here. And then we have our fundamental theorem, f prime of x dx a to b. This one's very crucial for what follows, f of b minus f of a. So those are our basic calculus ideas in a nutshell, right? For one variable. So what about multivariable? Multivariable is going to come into play. Here we already had, when we were talking about this temperature was a function of in free space. Let's go ahead and write that down, what we had here, just to be complete. We had t was a function of x, y, and z, and time, right? A scalar field, and this was all, you know, all of space or a subset of space. This was the time, this was the partial derivative only with respect to time. And this del squared in Cartesian coordinates, just to return to that, that was d squared dx squared plus d squared dy squared plus d squared over dz squared. And the steps I took the other day in obtaining this differential equation involved integrations and integral theorems as well. So there was actually a whole world of stuff going on there. And what we're going to do is just systematically work our way through that. This material you get in a lot of places in physics. So in classical mechanics, we're going to be doing this stuff in E&M, 107A and B. That's where you really hit this material the most thoroughly. So, and it's important to see it often, see a lot of it. And you will. Okay. But at this point, how much multivariable calculus do you guys have?
One class that maybe dealt with it.
One class that dealt with it.
I suppose.
How about the rest of you guys? One class? Half class?
2 classes.
But you haven't seen much of it in physics yet, I'm guessing.
No, just in a pure math context.
And what about in 4B? Did it ever come up or just slightly? Integral theorems. Remember Gauss's law? That was Gauss's law. Anyway, that's what we're headed. We're gonna.
We used Gauss's law, but I don't think we really went into the underlying logic of why it worked.
Good. Okay. Yeah. So I want to mention all those things, and like I said, you'll see them more than once, and they're just fundamental to your whole way of thinking as a physicist. So one of the great things about physics, we don't learn this stuff in order to forget it, but you know, we use it repeatedly. So anyway, let's start talking about functions of many variables and these operators that operate on them. So the next thing we'll do is we'll take functions of 3 variables, f of r, f of x, y, and z. And we have, in place of the first derivative of a function of one variable, we have the gradient of r. So the gradient operator looks like this, gradient f, and it turns a scalar into a vector. So its definition here, Cartesian coordinates, would be partial f with respect to x, and that would be one component. So I'll do it in I, j, and k. Partial f with respect to of course, do an ordered triple as well. We want to, I go back and forth between those, depending on what we want. So, you know, this gives us the well, if we're just taking one, you know, it's just the first derivative, right? We have just one variable. Take all three of them, you're getting a direction, and that's pointing in the direction of greatest increase. Okay? Just like a first derivative does, but now it's in 3 dimensions. The functions to practice this on that are not contrived. So the example that we're going to use so much is U of R equals minus alpha over R minus alpha over the square root x squared plus y squared plus z squared. So we're just treating it in Cartesian coordinates right now. Because we know what this thing looks like as a function of R. It's thought about as a function of R, it looks like that. And we have for gravity, we have for Coulomb's law. Well, Coulomb's law with both signs, for gravity just with let alpha be positive, like that. So, and we've been dealing with this as a function of one variable at the very beginning of the semester, right? We expanded it, we know the direction and so forth. So what about this gradient here? So we want, so now we'll have the gradient of this U of R as our first example. And that will be, and in fact, I could even remind us in physics, negative gradient of U of R would actually be the force, right? Or it could be the electric field. Let's just look at the gradient of U of R right now. Okay? So we have d dx negative alpha over root x squared plus y squared plus z squared times I hat. And the other two are going to be the same. Replacing x's with y's and so forth. So we'll just focus on this one right now. We've got a minus alpha. We've got this root to the minus 1/2 power. So we have minus 1/2 this thing to the 3/2 power. So I'm going to write x squared plus z squared to the 3/2 power. And now I have a chain rule, and that'll be the inner derivative here, so that'll be times 2x. And when the dust settles, actually, we'll keep this line down here. So when the dust settles, the 2's have canceled. Okay. We have a minus times a minus, so that's now a plus. And we have x over this thing to the 3/2 power. So this is actually x over r cubed. Just give it a couple steps, leave a little bit of space in there for yourself, okay? Leave a little space if you want to.
Where's the alpha?
And the alpha is there. Right? Because this was the 1/2 power, and that was the r itself, right? So if it's to the 3/2, it's r cubed. I hat. And yeah, this is a nice thing about a calculation like this. If we did this with respect to y, the only thing would change that we would have alpha y over r cubed j hat plus alpha z over r cubed k hat. So we actually have our entire vector there. We did one derivative. We got all three of them. Let's interpret this thing a little more. And another thing we can, or, yeah. I'll just put here as a note. If R is X, Y, Z equals X I hat plus Y J hat plus Z K hat, sometimes it's nicer to use my form. Then R hat is R divided by its magnitude. And so what I have here is an alpha over R squared times R divided by its magnitude, okay? Because that R squared, which is the third power, and of course, this is that unit vector. And what did we just find? We have the gradient of the one over R potential is the one over R squared force, essentially. Now, if we're doing physics, we could say, well, we wanted the negative gradient of this as being force, and that gives you the direction. So this vector here is pointing away from the origin, and then put a minus sign on, it's pointing towards the origin, and we're talking about attractive force. So there's the math of that, and there's also the physics right there. This would be gravity or electrostatics, right? Yeah, so I use this right there. So there's your gradient operation, and you know, its most important application. And what comes next here is the chain rule. Anything else to say about this? What more to say about this one? We'll leave this here for now. I'll just put this as a note. If F equals minus gradient of U, as we have in physics, then F equals minus alpha over R squared R. For R, this is a unit vector, so we have attraction or force towards the origin. And the force is directed towards the origin. Towards the origin. Well, you see the nice interplay between the function that we started talking about this semester, right? Just as the one over R, and then the whole vector physics that goes with it. Okay, good. So that's the gradient. We immediately need to talk about the chain rule. And the chain rule in multivariable calculus, I've looked this up and it's never proven in the elementary textbooks. It's just given as a rule. In order to get the proof of that, you have to have some linear algebra. I'm gonna make it up to you later. We'll get the proof of the chain rule. But right now, I'm just gonna give it to you as a formula. And it's easy to remember as well. Comes right out of the standard chain rule. So chain rule. So next we have the chain rule for f of x, y, and z, right? So we've got our f of r, we want the chain rule. And the typical application is we have f, we have f of r of t. This would be something we have in mechanics all the time, where a function of the position of a particle that's moving. in time. But this, of course, could just be a parameter. But yeah, suppose we want the derivative with respect to time of f of r of t. Okay. So what we'll do is we'll say the time derivative of f of x of t, y of t, z of t, and leave a little space. Well, we'll just do the first one. df dx of dx dt. So far so good, right? And the chain rule for multivariable is just to add these individual ones. Literally just add them up linearly, so plus df dy dt plus df dz dt. So the chain rule is just that summation. But it has something else going on here, because we have this combination of those three partial derivatives, and we have these three, in this case, velocity components. So this can actually be interpreted as a scalar product of two vectors. Okay? So it's the scalar product of the gradient of f of x of t dotted into, I'm using r here, so let's be consistent. Dotted, so r of t, let's just expand it out. Dot product with this dr dt. This comes up all the time, chain rule. And in fact, we generalize it to n variables immediately as well. So the gradient of f dr dt, and in physics we'll often see this then. We could say the differential of f is equal to the gradient of f dotted into dr like that. And this is where that comes from. Okay. So yeah, scalar product. So with these two, we can already do a fair amount. I think I'll do the integration discussion before we do curl and divergence. So just with gradient, and of course the idea here, this r of t would trace out a path in space. Okay. And if it were not time, it could just be a parameter. I could call it tau, and then I'm no longer doing dynamics. I'm just giving the parametrization of the curve in space. So let's go ahead and take a look at that. So the chain rule. Actually, let's add many variables. What I can do is say, good, x vector is x1 all the way to xn. So now I have n variables, and I could be in n space, and I could have x vector is the vector as a function of tau, so that would be the parametrization of a curve. What's an example we had over in mechanics recently? Parametrization of our favorite curve. The cycloid. Right? The cycloid's on everyone's mind this week. Everybody solve that problem? I know one person probably solved it. So the cycloid is an example of a, of parametrization. Example, we had, x of theta equals r theta minus r sine theta. I'm going to slightly different nomenclature. R minus then our parameter is theta, and we can change derivatives and so forth. It's something we're moving along that. Okay, so for many variables, we go ahead and complete this thought. What's there? So for many variables, we could have and dx, d tau would be the sum, since now we're going n of these, k equals 1 to n, the sum over dx back up. The sum over df dxk of x times dx of k d tau. Okay. And that again, that would be an n-dimensional gradient dotted into an n-dimensional velocity type of vector, or tangential vectors, what we call them. So that, and we get really used to this kind of summation here and recognizing where it came from. Okay. Good, so that's for many variables. Now let's look at the integration theorem that would go along with this. This is a good way to get started. So next, integration. And I'm just going to write down the fundamental one-dimensional integral, and then we'll see where that kind of an integral there. So integral of one variable, this is what I had up there a moment ago. So this time we can say integration n equals 1, and we had f prime of x dx from a to b equals f of b minus f of a, right? This is something we always use. And the picture, like I said, would be now I have a to b. I'm asking for the integral of the derivative. But you know, this is denominator, but here's my f of x there. Okay. So the proof of this thing is kind of interesting. So proof, or just the illustration of it, what we do is we approximate this integral here by f of x k plus 1 minus f of x k divided by x k plus 1 minus x k, because this is the difference quotient. If these things are close enough together, it's the actual derivative, right? And times xk plus 1 minus xk. So in the limit as so k equals 1 to n, I can even be pretty precise about this. I can say x sub k is equal to a plus b minus a divided by n times k. Right, that literally gives me all of the little points. As I make n go to infinity, I just make this delta x smaller. But what you have here, these two, of course, just cancel. Right, these two. And when you're all done, you have, give or take a number or two, 0 to, here I gotta adjust these things here. K equals 0, maybe k equals 0 to n minus 1. Okay. Yeah, because what's left is the last one and the first one of all of these. Otherwise, they're all canceling as I add this. So I'm left with f of x n minus f of x0, right, equals f of b minus f of a. So that's the construction, that's actually the Riemann sum. And that's this fundamental theorem vector. So we want to do this thing in 3 dimensions and even n dimensions. And in 3D, 3 dimensions or n dimensions, what we're looking for is the gradient, or we're looking for the gradient of f, which we know is a vector, dotted into dr, and we're doing this to 2 points in space, A and B. So now we have a point in space A, and we're integrating in some direction over to B. And this, of course, reminds us of what we're doing with complex contour integrals, right? This is literally, or not literally, but very close to the idea of the complex contour integrals. The contour integral here, 3 or n space. So this is going to be f evaluated at that point in space, b minus f evaluated at point in space, a. So that's the first of our integral theorems. What would the proof of this thing be? Well, right here, this looks like a perfect analogy. But what we can do is, I'll just put as a proof here, the following. Consider d over d tau of f of r of tau. So r of tau is my path here, my contour, my parametrization. Okay. And as I just showed you with the chain rule, this would be the gradient of f dotted into dr d tau, just by that chain rule. And then this integral gradient of f dot dr is going to be in the application, actually, it's going to be gradient of f dotted into dr d tau integrated over d tau. Okay. Now I would call this tau sub a and tau sub b. Those are the parameters at which we're located at points A and B. And if you look at this here, and this fact that's right above it, you know, this is an integral of df d tau tau sub a tau sub b equals f of tau sub b minus f of tau sub a equals f of, well, this is r of tau sub b, r of tau sub a, so it equals f of b minus f of a. So this is actually a direct application from our fundamental theorem here to the version of it that takes us along a contour in 3 space with a gradient. Okay. So all I used was the chain rule here. I think this is fairly complete. This should have actually, I could clean this up a bit. This should have been f of r of tau sub b minus f of r of tau sub a. So anyway, this integral along a contour is very important. And suppose you have a contour at A and end up at B, but maybe you just keep going and return to A. Then what? If it's an integral of this form, then it'll be f of a minus f of a 0, right? So that'll be the closed contour giving you a vanishing result. And we've seen similar stuff there in complex analysis as well. So that's the first one here. And the length of the curve actually, this is touching on what we did in mechanics, because when we did the length of the cycloid, we were using these ideas here. Okay. Good, so there's integration, and we've got the gradient, and we've got the chain rule, and we've got the integral theorem, we can say that goes along with it. So now the operators get a little more complicated. How's everybody feel about these? So these are pretty natural for us, right? It's kind of right in line with what we've been doing in the complex plane and in our parameterization. Okay, so what comes next in these differential operators is divergence and curl. So let's take both of those. So this next thing we'll call differential operators. In 3 dimensions. And the first one we already have, that's the gradient. So, and in some books you'll see it written out grad f, or the del symbol f, that's our gradient, is what we just talked about, okay? And this one takes takes a scalar and produces a vector, so from scalar f to vector gradient f. The next one we'll talk about is the divergence. So div f, okay, also del dot f. So that's going to take a vector and turn it into a scalar. So it's from vector f to scalar del dot f. So what we have here as a definition, the divergence of f of, all right, x, y, and z. So that's a vector of a vector position, or vector argument, vector function of a vector argument. So what you have here is d f sub x dx, or the first component, first variable, plus x, d f sub y dy plus d f sub z dz. So that's how it's turning, like I said, turning a vector into a scalar, and there's got to be that dot there, because it's like the dot product between, the other way, should we do this? Yeah, the vector we're talking about is d over dx, so this is an operator. Say we're taking a 3-component operator, we're taking that into the vector fx this is the rule here, if you wanna keep in mind. Since we already did this one over R potential, what about the divergence of that vector we just found? So divergence of alpha over R squared over R like that. That would be a good one. Because first we would just write its definition down. That would be d over dx. Here we would have alpha x over R cubed. What's d over dy? Alpha y cubed, and the same thing for z. D over dc. Alpha z over R cubed. And of course we'd have to say R is x squared plus y squared plus z squared to the 1/2 power. So now we have a bunch of chain rule and stuff, but we're just going to focus on this one. Okay, on the first one, the other two will just fall into our lap, the way this happened before. So we're doing a couple of things on this derivative. Alpha comes out front. So the derivative with respect to the numerator, we just have 1 over R cubed. Then we can also have, hold the x constant, then we have R to the minus 3, so we have minus 3 R to the minus 4, and then the inner derivative. So what's the inner derivative? What's the derivative of R with respect to x? I'm gonna put that right here, okay? So the dr dx is equal to 1/2 R to the minus 1/2. So just R. So 1/2, this is the minus 1/2 power, it's up in the denominator, and the inner derivative is 2x. So that's just equal to x over R. So we got 3x, and I have another x over R. Plus, and can we just write the other 3 down now? The other 2? We can. Alpha 1 over R cubed. Actually, I had a minus, did I lose a minus sign here? I did. This is a minus 3 power, so there's a minus. So we got 1 over R cubed. Minus 3, this time it's going to be y squared over R to the 5th. That's alpha over R cubed minus 3 z squared over R to the 5th. And this is a really interesting one. Equals alpha times, I'm going to add the 1 over R cubed 3 times, so 3 over R cubed. And then I'm going to have minus 3 over R to the 5th x squared plus y squared plus z squared. Now there's an interesting result. Everybody see the punchline here? That's going to be an R squared. So this is actually going to add up to 0. How great is that? It's 0 unless R is equal to 0, then it's undefined. So equals 0 for R not equal to 0. This one we're going to hold on to is going to be an important example. Yeah, fantastic. So there's an example for it. Okay. Of the divergence, and that's an important important stereotypical calculation that you'll recognize again and again. So in fact, what's really important is knowing this. Because this is a shortcut you'll use a lot. Okay, you use this shortcut a lot again and again. In fact, what this shortcut means is that the gradient of this function r itself, of this magnitude function, is equal to the unit vector. Okay, because I did it for x and I got x over r, moved for y, you get y over r, z over r. Okay? So yeah, that's a really important result. Okay, so there's the divergence. And you know you have more operators because you've got more going on in 3 dimensions than you have in 1 dimension. Okay. So who remembers the curl? Curl operator. And actually, let me say a little more about the physics of this. This thing could have been an electric charge, right? And then you'd say the divergence of the electric field is 0 except, at the source itself. Okay, so that's where that would have come into play. Who remembers the curl? The curl operator. Yeah. This one is memorable. Okay, I'll go ahead and leave this up here and continue my list. Get the curls done, and then that'll be a good. Okay, so we have this here. So in some of the other languages, the curl is also referred to as the rotation. But we'll call it the curl of F. And we also say del cross F as in cross product. And that takes a vector into a vector. So vector to vector. And yeah, because it has this definition of the cross product, you can do this. Curl of F, and then you line up in Cartesian coordinates that determinant. And here you have d over dx, d over dy, d over dz. And here you have fx, fy, and fz. And then if you remember that, then this one's no problem. So our I hat will have d fz dy minus d fy dz, as in I hat, and then this subdeterminant here, d dy fz minus that. Okay. And the j hat one will have d dz of fx minus d dx of fz. And the k hat one will have dx of fy minus dy of fx. So yeah, this thing looks very unwieldy. And it is. But again, it's a combination of first derivatives. So everything we're doing here, grad, div, curl, those are first derivatives applied in the world of scalar and vector functions of 3 variables. So what's the interpretation of this? Anybody remember that? This is a bad combination. So it's often, the Russians and Germans call it the rotation. And a nice example for this one is this following vector field. Consider we're going to do a vector field V of x, y, and z. And this itself is going to be a vector cross a vector like this. And this is the rotating bucket. Consider the rotating bucket. So what we're gonna do is let omega is equal to, 0, 0, omega like that. So the idea is that we've got a rotating bucket and omega is pointed here, and the cross product of this omega, say, with this r here, is a velocity. Right? It's a velocity, and for the one I'm drawing here would be into the board and so forth. Okay? Top view would be the omega is coming out of the board like this, and r is here, and omega cross r, I'll draw it in a different color. At that point would be the velocity vector. And the farther out you go, the longer the velocity vector would be, right? It grows up here like that. What about up here? So forth, okay. So the benefit of this example is that you can completely visualize it. Completely visualize it. I have a great idea for homework assignment. We didn't have anything for next week yet, right? Drew a line under what we had this week, must have been Thursday. So, okay, I'll calculate this one and then I'll assign a little generalization of it. So what we're going to do is, maybe I'll assign this. Well, let's get started on this. So the first thing we have to do is calculate this V field, and the second thing we have to do is take its curl. So we'll go ahead and write this down. 1, calculate V of x, y, and z. 2, find curl of V of x, y, and z. That's our plan. So all of this, some of this stuff. This cross product, so we've got V, V is equal to I, J, K, 0, 0, omega, x, y, z. I'm using the determinant form for the cross product. So the I hat is going to good. So the I hat, here we go, is going to be 0 times z minus omega y. J hat is going to be minus times minus, so omega x. And the k hat is going to be 0. So that makes sense, because that's in keeping with the top view, where we're just, rotating around that way counterclockwise. We're just gonna have x and y components. It's gonna be no z component. So that's good. So we can say v is equal to minus omega y hat plus omega x j hat. And then we'll plug this into the curl of V formula. And curl of V is going to be I, J, K, d over dx, d over dz, minus omega y, omega x 0. So what happens on this determinant is following. the I hat component, there's a zero, partial respect to z of omega x is also a zero. So we're getting I hat times zero. Same thing for j hat. You got a zero here, you've got a z, respect to I is a zero. So k hat must be the one, otherwise nothing going on here. So what do we have for k hat? D over dx, omega x, that gives us omega, minus d over dy, negative omega y, gives us another omega, omega plus omega. So the curl is only in k hat direction, so it equals 2 omega k hat. So we're gonna hold on to this, this result. And go to our picture. And so we can see what the curl really means. So the curl of this counterclockwise thing rotating is a vector that comes out. It somehow seems to have something to do with the rotation here. Okay, so the curl of this red field here, counterclockwise velocity field, is a vector that points straight out here. There's another interpretation of it. If you had a little paddle wheel, if this were a fluid, you had a little paddle wheel, then because the velocity is larger and the farther away you go, this little paddle wheel would spin. And if you had a fluid flow, if you put something in there, it would rotate the little paddle. So there's a very physical interpretation of this. So the rotating bucket, that field has curl, okay, it has a non-vanishing curl. Now here's a great homework problem. Gotta have at least one. At least one, here we go. So the homework problem is to generalize this, and we get also an interesting result. All these results we can build into some future theorems that we're gonna discuss. So let me erase, I'll erase this.
Tomorrow or next week?
For next week, yeah. This would be the only one for next week so far, unless I come up with something, if I come up with something fast. So the homework problem is to do a rotating bucket with a little modification. So modified rotating bucket. So what we're going to do is define our velocity field as an omega cross vector r divided by r to the n. And we're going to let r simply be a two-dimensional vector now. We don't need the z component. We saw right there before that we were able to just have a two-dimensional velocity field. So we're gonna let r be two-dimensional. So r is equal to, x I hat plus y j hat, so that the magnitude of r is just the root of x squared plus y squared. We don't want any z in the mix here, and we can dispense with that. And omega has the appropriate, omega is the same. Let me write this. So omega vector equals 0, 0, omega, just like we did before. And omega has the appropriate dimension, right? It's no longer just going to be the units 1 over time, because we have different lengths here, right? Appropriate dimension. We don't have to worry about it. So we have this, and we want to calculate the curl. all n. There's one value of n for which the curl vanishes, and that's gonna be physically interesting and mathematically interesting as well. This, by the way, is something that you see in electricity and magnetism when you're doing Ampere's law. It just have different letters, okay? Good. Let's see what else we can do here. And you know, while we're at it, so this will give us a second problem we can discuss on Monday if need be. So this one will also say, show that curl of grad of f is equal to 0. That's just a basic vector identity. Curl of grad equals 0. Just by direct calculation. Direct calculation. So, f is equal to f of x, y, and z. Then you have its gradient, then you have its curl, and that matches. Good, that's enough. That's all I've got for you today. So once we do this, we come back and look at the integral theorems of Stokes and Gauss and get a couple more applications. We'll be in good shape. Reasonably good shape. What do you guys think? All make sense? Good. Good, we'll call it a day.
So the only homeworks are this week were the residue theorem stuff.
Yeah. Those integrals. Were there any others?